Well, good afternoon, everybody. How is everybody doing? I hope you're having a wonderful day. Been a little rainy here, but you know what? We're going to work through it and we're going to make everything work out fine. So, today's class is on understanding schematics. So, this is kind of a follow up to the basic 101 class that we had. So, we're going to move start straight on right on to our next one is meter basics. Okay, so I will tell you that uh, there is questions for a quiz. Okay, so you need to pay attention and know exactly where, kind of pay attention to it and be able to answer the questions. Okay, so meters is designed to meet three properties found in a working circuit. Okay, they are there to measure resistance, voltage, and current flow. Okay, and your voltage can be either AC or DC. Okay, it'll also check amps, which is part of the voltage. Okay, so that's why it's called a multimeter. Okay, they can perform multiple functions and measure in different kinds of voltage, with currents being AC or DC. Okay, so what is resistance? Resistance is the opposition to current flow. Okay, a component has to be measured in units called ohms, which is, you need to remember that the symbol for ohms you see right there is the omega symbol. So all electrical components or devices have a resistance value. The symbol for ohms is, like I said, you see the omega symbol. Okay. Um, the examples is an inductor, a circuit board, a power supply board, a resistor, a diode. Those are all examples of things that have resistance. Okay, voltage, the electrical potential or uh, potential difference between 2 points is measured in units called volts. The symbol for voltage is V. Okay, the current can be either AC alternating current or DC direct current. I said those backwards, but it's still the same. An example of DC voltage would be a car battery that's in your car. Okay, AC voltage could be the 120 volts that's in your home, or it could be the 240 that's in your home, or it could be, if you have a different thing, it could be 308. So those are all voltage that it's measured. Okay, current is the flow of electrons through a conductor, which is a wire. Okay, at a certain rate based on the voltage source provided and the resistance that flows of current that flows into the circuit. Okay, circuit is amperes, so the current is measured in amperes or amps. Amperes are the long way to say it. Everybody that I know says amps. Okay. The symbol for current is the capital A. Okay. Just like voltage, currents can either be AC alternating current or DC direct current based on the voltage source in the circuit. Okay. An example of some AC voltage will be a light bulb in your room. When you put the light switch on to the on position, you complete the current path from the source, which is 120 volts AC fuse box, through the switch to the light bulb, and then back to the fuse box, which is the ground, the neutral side. Okay, the current uses AC current. Okay, the switch 9 times out of 10 switches today, they do not break the power leg; they break the neutral leg. That's something that you need to remember, but you need to double check it. My house that I have down in Daytona Beach, it has it's broken with the power leg. So the power leg is the one that gets broken with a switch, and that's not a good thing. Okay. So circuit values. These properties, they're found in every circuit. They can be large values or very small values. Okay. For example, a component's resistance can be in the millions of ohms resistance. A unit with a million ohms is called a mega ohm. Okay. If you have a very small circuit, okay, a very small value of current, and the resistance is opposing the current flow to the circuit that is very large. Sometimes the current measurement of the current can be very small. The units of 1/1,000,000 of an amp. Okay, this amp flow is also current flow is also called a microamp. Okay, the symbol down there, you may recognize that if you're a current technician. It's a microfarad. Okay, so if I'm checking a capacitor, that's what I'm gonna do is I'm gonna look at the microfarads to find out what it produces whenever it's energized. Okay, so let's go to the SI table of circuit values. Okay, if the prefix used is a capital letter, that typically represents a unit of measurement of 1,000 or greater. If the prefix used is a small or a lowercase letter or symbol, okay, that typically represents a unit of measure of less than one. It's a fraction. Okay, so if you look at the microfarads, okay, you divide it by 1,000,000, so that would be 10 to the minus sixth power. Okay, if I have a nano, okay, I'm going to divide it by millionths, trillionths, okay, and that would be 10 to the minus 9 power. Okay, so let's remember that. Okay, so moving along. Okay. Note if the prefix used is a capital letter that represents a unit of measure larger than one. Okay. So let's look at a tera, just like a terabyte on a computer. It's a unit of measurement. Okay. It's how much storage do I have in a terabyte unit? The unit that I have right here is a 2 terabyte unit. Okay, so I would need to know that this unit will hold one 10 to the 12th power. Two, I'm sorry, it would be 20 to the 12th power. Okay, so a gigabyte. Everybody's familiar with a gigabyte. It's what we mainly use today in most computers is a gigabyte. So you see that there's one um, uh, whatever times 10 to the ninth power. Okay. So, like I said, with a terabyte, it would be 2 times 10 to the 12th power. Okay. If I've got a nanobyte, okay, I'm going to divide by 1,000,000th. Okay. That is 10 to the minus ninth, not 10 to the ninth. That would be 10 to the minus ninth power. Okay. Table of circuits. This right here shows you a gigabyte. A giga is 10 to the ninth power, and that's a mathematical ratio of billions. And the symbol is a capital G. Remember, if you go back, okay, if you go back, whoops, if I go back and the prefix uses a capital letter, that is a representation of a unit that is measure amount is larger than one. Okay, so this would be 10 to the ninth power, and that would be your gigaohms. Okay, if I have any of the fractions using the minus power, okay, the milli is 10 to the minus third, which is thousands. Okay, micro is millionths, nano is billionths, and pico is trillionths. Okay, if you notice right here, we're talking about capital G, capital M, capital K. Okay, This is a table that provides the definition of each unit of measurement mathematically, 10 to the power. Okay, representation of value, mathematical ratio, prefix, the prefix of that unit used measure in word form. Okay, the symbol that represents the unit in the documentation, like build or parts list, schematic diagrams, etc. Okay, here's another look at it a different way. I prefer the other way. Um, well, look at that. Whenever I set all these up, they were all nice and straight, and this one just went crazy whenever I transferred it over to this slide. Okay, so a millionth volts is 1 to the 10th to the ninth power volts. Okay, which equals 1 gigavolt, which equals 1 GV. Okay. Examples of circuit values. The current circuit can vary greatly. Okay. Below are examples showing how the unit of value behind the number will significantly change the value of the unit the current meter reads. Okay. 1 millionth, 1 trillionth of an amp is 1 to the ninth power. That is a gigaamp. Okay. The 1 to the millionth is a 1 to the sixth power amp, which is a mega amp. If you notice, it's a one mega amp. Okay, and the next one is a kiloamp. Okay, this is whenever we all started out with. We didn't want to go to the system that everybody uses. We wanted to use our own system. But if you look, everything is actually, if you're doing voltage and stuff, you actually have to revert back to the worldwide, not the US. Okay. So once again, we have 1 to the 10th power, okay, which is a giga ohm, which is a giga ohm. Then I have 1 to the millionth ohms. Okay, that's 1 times 10 to the sixth power ohms. Okay, okay, and then I have 1 mega ohm. That's what that is. 1 millionth is 1 mega ohm, which is 1 to the. If you look at that, m to the omega symbol. Okay, so here's the first one of our short quizzes. Okay, there are 3 of these in this presentation. I need for all of you to answer whenever I go and they review all of the classes that I do. They actually grade me on having audience participation. So I need for you to help me by answering the questions down in the box, and answering the question. Okay, so the value behind how many you see that is, oh, I left out 1 0. No, I didn't. 1 millionth ohms is stated as what? A mega ohm, a kilo ohm, or a giga ohm. Okay, somebody answer that one for me. Okay, I'm gonna cheat a little bit. Okay, there it is right there. So what is it? I'm gonna take me a sip of water while somebody writes in. Somebody answer it for me. Come on, I just gave you the answer right there. Somebody work with me here. Okay, there it is. It's a giga ohm. Okay, the unit of measure mathematically power to the 10th for a kilo ohm is what? 10 to the ninth power, 10 to the third power, or 10 to the sixth power. Okay. For a kilo ohm, what is it? There it is right there. What is a kilo ohm? Okay, like I said, there's your kilo ohm. That's one. That is, excuse me, that is 10 to the third power. Okay, just like AC voltage. Okay, just like current, amps can be blank depending on the power source. Could be, is it AC? Is it DC? Is it both? Is it both of A and B, or is it none of the answers? Thank you, Sharonda. Appreciate it. Okay, so on question number 3, we have, just like voltage, current, which is amps, can be measured either AC, DC, both, none, depending on the power source. What's the answer to question number 3? Correct, both. Thank you. Okay, let's talk about our meters. Okay, so what really is my role as a circuit value? Okay, if you look right here, this is one of the old. I have one of these in a box somewhere that was very expensive whenever I first started back in 1978. Okay, I can buy that same meter today for about $6 and just as accurate as it was then. Okay, the meter's role is to accurately measure these units of measure. Okay, if an analog or digital or needle meter, okay, has only one range of measurement on its face, it could be very hard to get an accurate reading. In order to make things easier to get a very accurate reading, all meters use ranges of measurement. Okay, some meters have to be switched from range to range manually. Okay, when this when excuse me, this is when the user rotates the dial to the correct position. Okay, so the multiplier range, so that it will display the correct value. Okay, an example of the DC voltage range are 0 to -1 DCVs. So if you look down where it says DCV, you see a point 0. Okay, 0.1, you see 0.5, 2.5, a 10, a 50, a 250, and 1,000. Okay, so that would be my ranges. So if I'm trying to measure something that is somewhere between 0 and zero point 0.1 DC volts, I'll use that first selector. I'll spin that knob all the way down to the very bottom of the DC chart, and that's where I'm going to find my DC range. Okay, if something happens and I shoot 1,000 DC volts to it, and I'm on the point one DC volt range, what's going to happen to my meter? If I do it continuously all the time, I'm going to mess my meter up. Okay, so reading circuit values. Okay, this right here is the new meter that I actually have, and this one was a whole $5.68. Harbor Freight. Okay, does it work? Absolutely. This is the meter that I keep in my house whenever I'm going to have to go check something real quick. And I don't read it. I don't have to have something that is super accurate and great. Okay. I can use this and it works fine. This is the one that, like I said, I keep this one in the house. Okay. Can I measure can I measure what am I looking for? I can't measure, I can't put it in the oven and measure heat with it. Okay. This is just like DC volts, AC volts, ohms. Okay. That's all that this meter will measure. Okay. If a digital or numeric meter has only one range of measurement on its face, it would be very hard to get an accurate reading. In order to make it easier to get an accurate reading on all meters using ranges of measurement, some digital meters are switched from range to range manually. This is when the user rotates the dial to select the proper multiplier range so that the meter can display the value so that the reader can read it properly. Okay. In this example, the DC voltage ranges are 0 to 0.2 DC volts, 0 to 2 DC volts, 0 to 20 DC volts, 0 to 200 DC volts, and 0 to 1,000 DC volts. If you look at this one DC volts, okay, it shows exactly right there where it is. So I'm going to have to select that with every one of my meters. Okay. So if you look at this different meter, I do not have one of these. I don't really use this one. I have a different one that I use that I like a whole lot better, but we're going to get to that one in just a minute. Okay. The meter's role is to accurately measure these units of measure. To make it easier to measure in many of today's multimeters, digital or numeric meters have an auto range filter feature. Okay. In this configuration, the meter senses the value of the property being measured, and it will adjust to the proper range to provide an accurate reading. The meter to the right is an example of an auto ranging meter, so you can properly meter only allows the user to select the property they want to measure, but there is no ranges that they have to select. Okay, as we have gotten more sophisticated, they now use auto range meters. Okay. So the meter's role is critical to remove the operating power source from the unit before being diagnosed. Okay. The first thing that I always tell everybody is if I'm going to measure something that is not current related, whether that be amps or volts, okay, I do not want the unit plugged in. If I try to measure something with the excuse me, on the if I'm trying to diagnose something, the most common method is to unplug the power outlet, turning the unit off the power appliance's power at the circuit breaker box. Okay, if I'm trying to measure resistance, I will blow my meter up if I have it plugged in. Okay, mine in the one that I like to use, I have a little fuse in case I get stupid one time and forget to do it. And I have blown that little fuse a couple of times because I got in a hurry. Okay. We want to make sure that everybody's safe. Okay. As you see, this one right here has a battery. It does not have a fuse. You'll blow this meter up if you have it plugged in. Okay. If you look at this, shows the path for the common. Okay. It flows through the meter and it goes out to the other side. Okay. Measuring resistance. Once you have removed the power, you can use the meter's ohms function when the meter's internal battery to check the component's resistance value. Okay. If you notice, this is set to ohms. Okay. That's my resistance measure. Okay. This is the one I'm telling you, if you put it in ohms and you hook it up and it's got power, you're going to blow the meter up. Okay. So measuring resistance. What I used to always do, if I have a fuse in this manner, I always remove it from the system and I check it. Okay. If I get a zero, okay, in it, if I measure less than 1 ohm, I've got a good fuse. Okay. If I have a bad fuse, I have infinite resistance. Okay. Okay. One component that can have resistance checked functionally for functionality would be a fuse. A fuse would show the minimum of less than 1 ohm value of resistance. A bad fuse would show infinite resistance. Okay. Using the continuity function, okay, we're still talking. Okay. We're still talking about resistance. We're talking about the continuity, another word for it. Okay. Another feature on most multimeters can be used to check for low resistance on the continuity function. By using the beepers function, the technician can check low resistance components like fuses or coils to ensure functionality without seeing the meter's display. If the component is good, low resistance, then the meter will beep or get a tone. Okay. Mine has a tone. So mine didn't just beep. Mine had a tone. If I went between both sides, it beep. It'd be until I remove it. Okay. If I get no beep, okay, that tells me that it's not any good. It means that I have a failure. Okay. Here's a perfect example. This is using a magnetron on a microwave to check continuity. Okay. So if I check between here and I get the beep, what does that tell me? It tells me I got a good one. Now I can tell you right now, just because you get a beep, that doesn't mean that magnetron is good. I have run into them where they were just about to go bad, and I got a good continuity check. I got a beep, but it was bad. So you have to be very careful whenever you're checking a magnetron. Okay. So the one on the left is good. The one on the right is bad. If I'm looking at this one and I get nothing, it's bad. Okay. Checking a temperature sensor. Another component, okay, that you can use in its functional state is a temperature sensor. Samsung uses it on their refrigerators. Okay. Everybody is starting to use it all the time, but Samsung has been using this for I used to work for Samsung back in 2008. So I've been working for them. That's whenever I started checking temperature sensors. Okay. As the temperature that surrounds the sensor goes down, this is very important. Okay. As the temperature that surrounds the sensor goes down, the resistance value of the sensor goes up. Below is an example of checking a sensor from the main board as a component out of the unit. You've got to remove this unit. Okay. So the temperature sensor chart on the right shows how the sensor's resistance and voltage changes as the temperature surrounds it changes. Okay. So if I'm looking at this and my temperature is 35.6 degrees, my resistance value, okay, 12.2. My voltage is 2.75. Okay. As opposed to if I come over to, if the temperature is 77 degrees, say I have a bad sensor, I'm going to look at it. It's going to be 77 degrees outside. My resistance should be 5, and I should have 1.6 volts. Okay. So this is very important to remember, because this is not what you would think. Okay. Just like this says, okay, the sensor chart shows that the sensor's resistance and voltage values change as the temperature that surrounds it changes. Okay. As the temperature is 2.20, okay, the resistance value is 30.9, as opposed to if the temperature value is 35.6 degrees, my resistance value is 12.2. Okay. So my voltage is 3.78 in the first example. In the second example, it's 2.75. Okay. So as the temperature rises, okay, the resistance, what happens to the resistance? Once again, okay. So let's move on. Measuring voltage in a circuit, like resistance, a volt measurement is taken across the component or between two measurement points to check a circuit's functionality. When measuring voltages, the power on the circuit is from an external source, like 120 volts, okay, from a kitchen outlet, not from the meter, okay. So as you see here, he's got the meter plugged into both the sides. We've got one side of the power, and then one is the neutral. Okay. If I'm checking voltage to check a circuit, this is an example. A technician is checking 13 volts DC. Okay. On the power mode supply, is working after the unit was powered on. Okay. So one of the things that I will actually add into here, if you look at the size of the wire itself, you look in this example, he has 1, 2, 3. He has the meter on the 4th pin. Okay. If I look at the size of the wire, I see that is a very small wire. That tells me right away as a technician that I am going to be dealing with DC voltage. It's not 100%, but you can nearly about bet that it's DC voltage if I've got a small wire. Okay. Here is the meter that I use whenever I walk into a house. I carry this meter with me. Mine is a little more sophisticated than this. I can measure temperature, like in an oven. I can measure it. It's the meter that I use constantly. Okay. I can measure everything that I need to measure on with this meter. Okay. If I need to measure if I need to measure an igniter in either a range or in a dryer, I can use my clamp-on amp meter. Okay, that will actually tell me how many amps I'm pulling. So I have to set it to the amp circuit. Okay, a current draw measurement on a dryer igniter circuit. An example would be measuring the current using the clamp-on amp meter would be measuring the current that's being delivered to the dryer igniter in order for the dryer igniter to heat the igniter and to have have it activate the valve so that it opens and you get gas flow. Okay. To measure the current, you would open the clamp and surround one of the igniter wires. You don't do both of them, just one side. Okay. The clamp uses an induction sampling and will turn it into a converted. And that is in turn converted into corresponding current draw. That would create an inductive sample produced. Okay. So I am usually looking for somewhere around 3 to 3.4 amps, 3.5. I'm sorry. Um, Somewhere between 3 and 3.5 for that to come on, for that to ignite the flame, the gas with the gas valve. Okay. Here's an example of the clamp on here. This is the one that I tell you that I use all the time. I just grab one of the wires, check it. I see it whenever the fire, it will fire at about 3.5 amps. At that point, the voltage goes away from the igniter and it stays on. As this unit cycles, I'm once again gonna have to check and make sure that I get the correct amperage draw. Okay. Here is our another short quiz. Okay. If an analog or needle meter has only blank range of measurement on its face, 2, 1, or it has infinite. Okay. Who can tell me what that is? Sharonda, can you give me a hand here? It looks like you're the one that's going to be answering it, because it doesn't look like any of your other counterparts are going to actually answer it. Okay. If an analog or needle meter, okay, if we're using that, it only has what range of measurement on its face? Is it 2? Is it 1? Or it has infinite? Come on, guys. Give me a hand here. Okay. The answer to that is 1. Okay. To measure the current draw on an igniter, you would measure the current. You would open the clamp and surround one of the igniter wires. To measure the current, you would open the clamp and surround both the igniter wires. You have to measure it from the board. Okay. Which is the answer? Okay. Question 2. What's the answer? I made sure that I purposely stood out, made that one stand out. Come on, guys, give me a hand. Now we have 7 people. Okay. Somebody give me a hand here. Sharonda, I hope I'm pronouncing your name correctly. Do you know the answer to that one? Okay. The answer to question 2, the measurement to measure the current draw on an igniter for a gas, for something that's gas, I would surround one wire. Okay, not 2, 1. And you can't if you try to measure it from the board, you're going to get messed up. Okay. Okay. As the temperature that surrounds a sensor goes down, the resistance value of the sensor goes up, goes down, or remains the same. Okay. What's the answer to number 3? Okay. That's all part of this chart over here that we went through. Well, now I have messed myself up. Be still. They're right here. Okay. The sensor temperature on the chart. Okay. The temperature that surrounds it. So once again, if the temperature goes down, what happens to my resistance? So let's take the example in the center. Okay, that the temperature is 35.6. My resistance is 12. If my temperature drops to 2.20, my resistance goes to 30.9. What does that do then? So what does that tell me? Okay. Okay. Once again, I'm going to do it one more time. Somebody give me an answer. Okay. If my temperature goes down, my resistance goes up. Look there, 35.6 degrees. The resistance is 12.2. If my temperature drops to 2.2, my resistance is now up to 30.9. Okay. I realize that some of you guys are working around an appliance, but please do me a favor and at least put something in it, even if it's wrong. I had a gentleman do it, yeah, on Tuesday, and he got one answer wrong. But you know what? At least he answered the question. It made sure that I made sure that at least that I knew that he was understanding the what I was trying to give him. Okay. One of the components that can have resistance check for its fixed functionality would be a fuse. If the component is good, okay, if I have low resistance, then the meter would beep or give me a tone. Like I said, mine gives me a tone, it's not a beep. If the component has failed, the component resistance no longer a low value, the meter will not beep or tone. Okay, it's that the meter won't beep. Okay, it won't do anything. The definition of Ohm's law. If you're going to use anything that has to do with power, okay, or ohms, okay, Ohm's law states, okay, the relationship between electric current and potential difference. The current that flows through most conductors is generally proportional to the voltage applied to it. Okay, who did this? George Simon Ohm, who is a German physicist, and he was the first to verify Ohm's law experimentally. Okay. Once again, if you're going to just break it down to the simply stated, Ohm's law states that voltage across the conductor is directly proportional to the current flowing through it. Okay. It provided that all the physical conditions and temperatures remain constant. Okay. Why is Ohm's law so valuable? Okay. So it's kind of like the Pythagorean theorem. Okay. A squared plus B squared equals C squared. Okay. The part of the hypotenuse. If I have two of the values, okay, I can find out what the other value is. Exactly the same thing at whenever I'm using this for reading a schematic. Okay. Okay. If I have V, the voltage equals I times R. Okay. If I have the resistance, that equals the voltage over I. Okay. So once again, V equals IR, where voltage is the voltage across the conductor, I is the current flowing through the conductor, and R is the resistance provided by the conductor flowing through. Okay? So once again, it is directly proportional to the current flowing through it, provided all conditional physical conditions and temperatures remain constant. And in certain temperatures, okay, in certain components, increasing the current raises the temperature. An example of that is a filament in a light bulb, okay, which is the temperature rises as the current is increased, okay. If you think about your old incandescent light bulb, okay, if you leave that on for a while and it gets warmer and warmer and warmer, and pretty soon you can't touch it. Okay. Once again, let's go back over. Voltage equals the I, which was what was the I? Once again, I thought it was 2. Okay. V is voltage, I is current, and R is resistance. Okay. So I can figure out anything if I have 2 of the 3 items. I can figure out exactly what the other component should be. Okay. V equals I times R. I equals V over R. And R equals I over V. V over I. I'm sorry. Okay. So here's a short quiz on Ohm's law. Ohm's law. Okay. Ohm's law states the relationship between the electrical current and potential difference. Okay. What is Ohm's law? Is it V equals I over R squared? Is it E equals MC squared? Is it mass equals A squared plus C squared? Okay. The answer is A. Okay. Who was it that actually developed Ohm's law? He was a German physicist. What was his name? Was it Albert Einstein? Nope, don't think so. And Lipicus? That is not correct either. And George Simon Ohm is the correct answer. Okay. We're gonna move a little bit. We're gonna talk about a microwave. Okay. Microwaves. They are electromagnetic waves that lie in the frequency band between 300 megahertz and 300 gigahertz. Remember MHz and GHz. So mega HZ is hertz. So that M would be megahertz, gigahertz. Okay. The wavelength range of microwaves lies between 1 meter to 1 millimeter. Okay. In the electromagnetic spectrum, the microwaves are located between radio waves and infrared waves. Okay. Microwaves are advantageous as they consist of a large bandwidth that allows for easy transmission of bulk data. Also, microwaves are rarely affected by sky noise. Okay. There are certain instances whenever that is not true, but that is very rare. Most of the time, they are not affected at all. Okay. So this is why a microwave does what it does. Okay. That's why they came up with this, with a microwave. Okay. One of the major applications of microwaves can be seen in kitchen appliances, such as a microwave oven. The magnetron present in the internal circuitry of the microwave oven um, is the source of the microwaves. These emitted radiations get reflected on striking a metallic surface and get to absorb by food particles. Okay, this is the property of microwaves is utilized to heat and or cook food. Okay, that's the whole purpose of a microwave is to either reheat or cook. Although most of the time, if you're not using the right thing, you get a lot of uh, rubber tasting. Okay, so let's talk about energy consumption. Air conditioning, it uses about 60% of the total electricity that's in a home. Okay, they are very power hungry. So as we go through, we're going to talk about a couple of things that we literally on the spectrum. One of the things is a refrigerator, but if you look, total energy consumption is 16%. So if I'm talking about, let's talk about a refrigerator. That's 6%. That's 10% less than an air conditioner. Okay, a space heater, a water heater. Water heaters have gotten better, but this is the old stand in the right. Usually, it's right next to the washer and dryer. Okay, microwave televisions or consoles. Most people don't know what a console television is, but it used to be it was a television that had a usually a turntable, an 8-track tape player, and just a radio. That was a console television. Those are at 4%. Your computer uses about 2%. It's the reason you always want to turn it off. You're still using a lot of energy. Okay. So, what exactly is a wiring diagram? A wiring diagram is a virtual representation of physical connections and the physical layout of an electrical circuit. It shows the electrical wires and components are interconnected and can be also shown where the components are connected in the system. Okay. This right here is an example of a board. Okay. The only thing that I can do, I can't tell very much from this side. I can't get any readings or anything else from this side. I have to go to the other side to be able to check anything in there. Okay. Here's the back side of the PCB, and this is where I can take my readings from if I needed to. Okay. This right here is the what that's what a schematic looks like. So this right here would be the microcomputer board. Okay. That would be this board right here. Okay. As you well see, there's transformers, low voltage transformer right here. Actually, I got to go back to this one. Okay. There's my low voltage transformer right there on the bottom. Okay. So right here are all of the switches. There's a thermistor at the bottom right here. Switch. Okay. So our last quiz: microwaves are electromagnetic waves that lie in the frequency band of 300 gigahertz to 600 megahertz, 900 megahertz to 1200 gigahertz, or 300 megahertz to 300 gigahertz. Okay. Somebody give me a quick answer to that one. What's number one? What's answer to question number one? The answer to question number 1 is C. It's 300 megahertz to 300 gigahertz. Okay. I have to go back to the other thing so I can actually read that because my eyes are getting old and I can't see well. Okay. The wavelength range of the microwave lies between 1 meter and 1 millimeter, 1 meter and 1 meter, 1,000 meters, and 10,000 meters. Okay. This is the wavelength of the microwave. Okay. Where was that? I'm going to go back and show you right quick. Come on. Okay. It is right here. The wavelength range of the microwave lies between 1 meter and 1 millimeter. So that's the answer to the question. Okay. A wiring diagram is a blank. It shows how the electrical wires and components are interconnected and can also show where components are connected in the system. Okay, the wiring diagram is a useless item. It shows pictures of the boards, or it's a visual representation of the physical connections and the layouts of an electrical circuit. Okay, what was the answer to that one? Okay, what was the answer? It would be C. Okay, so does anybody have any questions over what we went over? Okay, this is going to conclude our program, and I really appreciate everybody working today um, with me. Um, I just need to make sure that everybody gets it. The one thing that that I have to always stress: please be safe. If you have any questions, unplug. Do not try to use it hot unless you know exactly what you're doing. You will electrocute yourself. Or if it's really bad and you get the right jolt of electricity, you can actually kill yourself. Okay. 110 voltage tends to hold on to people. It makes you want to hold on to the voltage. 220 will actually help you throw it. It pushes you away. But with the 110, it actually draws you in and you will electrocute yourself. All it takes is a couple of small things, a little water it will kill you. So please be careful out there. Anytime that you're going through schematics and you're checking, make sure that if you're not checking for voltage or amperage, that the unit is unplugged. I want to thank everybody again. I appreciate everybody. Have a great afternoon. It was a pleasure.